This is the 15th lecture of the course MTH 204A for section B. In the last lecture, we have proved that every P group is nilpotent. In fact, P groups are the building blocks for finite nilpotent groups, in the sense that a finite group is nilpotent if and only if it's a direct product of P groups. This is what we will prove in this lecture. So, to begin with, let me first prove the easier side. So, let me prove the following. Suppose H and K are two groups, nilpotent, then so is their direct product. And once you can prove it for two groups, then by induction you can extend that for any finite collection of nilpotent groups. And as a corollary, so before we prove, let me just immediately deduce the corollary from this. Proof is, suppose we are given G1 up to Gk such that order of Gi some p to the power ni for all I 1 up to k, and pi and each pi is prime. Of course, ni is a natural number. If this is so, then this is nilpotent. This is an immediate consequence of this proposition, which is yet to prove. And as I said, that later on what we are going to prove is, if a finite group is nilpotent, then it must be isomorphic to a product of this form. Okay, so first let me prove this proposition. Proof of the proposition. Proof of the proposition. So how do we prove it? The way is very simple. From H cross K to, okay. So in order to show some group is nilpotent, we have to take the consider ascending its upper central series. So we prove okay. So before that, let's first see. So the identity this trivial subgroup of this Cartesian product is the Cartesian product of the corresponding trivial subgroups. Now what about the center of H, center of this Cartesian, center of this direct product? It's nothing but it's easy to say it is the direct product of the centers. So basically we are going to establish that in the generality for every n greater or equal to 0, Zn of H cross K is Zn H cross Zn K. Okay. So if we can show this, then from that the nilpotence of H cross K will be immediate, because for sufficiently large n both the things will be, both of them will be, so this one will be H and this one will be K. So we are done. So we would like to show this, and how do we show? We prove this by induction. We prove this by induction. So okay, so let's first observe that for whatever n we have, this is what we have, we can consider Zn. Okay, let me first do it in this way. So okay, so here the map is the most obvious one. Some H comma K goes to H Zn H, this here, comma K Zn K. Now there is an isomorphism between this and in fact this follows from the very general property of direct products. Let me recall that here. Suppose we are given two groups G1 and G2, and H1 is normal subgroup of G1 and H2 is a normal subgroup of G2. Then of course H1 modulus is easy to see that H1, this is a normal subgroup of G1 G2. Furthermore, it's easy to see that this is isomorphic to G1 H1 G2 H2. How to see this? So basically consider this map from G1 comma G2 that goes to G1 H1 comma G2 H2. Okay. This map is easily seen to be a homomorphism because each component is a homomorphism, and then the kernel of this map is precisely this subgroup. So we have to have this isomorphism. Okay. So from here to here we do have this map which sends H comma K. It sends H comma K to the following subgroup Z and H cross Z and K. Okay. And let's assume for n that, so we want to run induction. So therefore we would like to assume it for n. For n equal to 0 or 1, this is obvious. So let's assume for n let's assume this for some n. So then we are having what we are having is precisely this. Okay. Now what is the map here? Again the obvious one, because we have say assumed that this is equals to this. So this is nothing but H comma K times Zn of H times K. So again let me tell you that I am proving by induction. So let's assume this statement for n. From that we will derive for n equal to 1, and for n equal to 0 this is already obvious. So then it will be proved for any non-negative n. Okay, so now you see that if you take the composition, you see that sends H comma K to this. So therefore from here to here this is nothing but the quotient map, right? Here there's nothing but the quotient map. Now in order to talk about Zn plus 1 of Hk, what we have to do is we have to take the center of this group, then pull it back all the way to here, right? So the center of this is same as center of this. Now once we bring back the center here, what do we see? It will be nothing but, so if I call this is psi, and if I call this is pi, then what will be psi inverse of center of this object, psi inverse of center of this quotient, which again you can write as without any problem, you can write as simply what is the center of, what is the inverse image of that? It's easy to see. When it comes back, it will be simply center of okay. That's quite clear, because whenever we are having this some isomorphism, center of that, the pullback of the center is the center of this. So this is what we are having, easy to see. And then now the next work is to pull this back to H cross K by pi inverse, and there's again another immediate verification that this is nothing but, since the map is component wise projection, this is nothing but Zn plus 1h times because the pullback of this inside is Zn plus 1h. Okay. So this is the pullback of the center to this thing. So therefore by definition this is nothing but Zn plus 1 of h cross k. Thus we are done. Since h and k are nilpotent, so when n is sufficiently large, this will be h and this will be k. Henceforth, we will get that from that n onwards for such a n, Zn of h cross k will be simply h cross k. Okay. This shows that the product of two nilpotent groups is always nilpotent, and that can be extended to finitely many such groups by induction. As a corollary, we see that the direct product of P groups is always, the P's might be different, direct product of P groups will always be nilpotent. Okay. Now let us try to prove what I keep on saying from the beginning, that is a finite group is nilpotent if and only if is a product of P groups. So the main theorem that we are going to prove is the following. So let G be a group whose order, let me write it as P1 to Pk to the power alpha k, where Pi's are primes and alpha i's are positive integers. Okay. The following are equivalent. What are the following statements? The first statement is G is nilpotent. G is nilpotent. The second statement is H is the normalizer of every proper subgroup. If a subgroup is proper in G, then it has to be proper inside its normalizer as well. The third statement is let Pi be the Pi Sylow subgroup. So remember that what it means by this is for the by Sylow's theorem there is a subgroup of order Pi to the power alpha I. Let us denote this by capital Pi Sylow Pi subgroup. Sylow Pi subgroup, then Pi has to be normal for each I. So the third condition says that all Sylow subgroups will be normal. The fourth one says that, I mean if we retain the notation from the third condition, G is isomorphic to the direct product of all Sylow subgroups. Okay. These are the following, we are going to prove that these four conditions are equivalent. Okay. Now in order to prove that, first we will do this, so the way we will proceed is we will prove from 1 to 2, 2 to 3, 3 to 4 and then 4 to 1. So 4 to 1 has already been done because each Sylow subgroup is having order some power of a prime. Therefore 4 to 1 is already there, we have to do 1 to 2 and 2 to 3, 1 to 2, 2 to 3 and 3 to 4. Okay. To do 1 to 3 we need the following lemma. Basically the lemma is nothing but it says, basically it proves 1 to 2 directly, that the lemma, again this just again you may not call it lemma because it is basically the statement of this lemma is exactly what we are proving, I mean exactly the statement 1 implies 2, however we can put it as a lemma. G is nilpotent. G is nilpotent. Okay, G is nilpotent, then if H is a proper subgroup of G, then H has to be a proper subgroup of its normalizer. So how to prove that? So it is a proper subgroup of G, therefore so let we choose let n be the largest index. You have to use that G is nilpotent such that Z and H is contained inside H. Remember that of course there will be one such n because Z0H is the trivial subgroup, it is contained inside H. So it is safe to talk about largest index such that this happens, and from the large thing, since n is the largest index, so Zn plus 1H is not going to be contained inside H. That means there exists an A or yeah, so that means this is non-empty, right, this is non-empty. Now what we do is we pick an A from this collection, okay. What we are going to show is the rest of this argument will hold for any A lying here. Sorry, I think Z will be ZZ. Okay, so what do we have about that? So what is Zn plus 1z? If you remember that, Zn plus 1z, quotient Znz is nothing but the center of the, so let me again write Zn plus 1z, Znz is nothing but the center of z modulo Zng. So being the center, this is an abelian group, therefore it is now quite clear that, sorry, here in the beginning I have to do that, yeah, fine. Therefore we have the following. So what do we have? So therefore for every h in H, one must have that AH of Zng is same as HA of Zng, because A Zng is in the center of G modulo Zng, right, fine. So that immediately shows the following, that is so what is this? This is nothing but A times Zng because of the abelian thing. Why does it true? Let me, yeah, so maybe I can do it. This is what we have here, and AH. Yes, I think the better way of doing this is just a minute. This is what we have. So on the other hand, this is nothing but A Zng. Okay, we must have this, and from that what do we obtain? So Zng is contained inside H. So hence we obtain there is A inverse H A lying in H. Okay. Yeah, so this is what we have because of this, and hence A inverse HA, A will be contained inside A inverse HA will be contained inside H times Zn I think this step is basically, it is to be put on the above, yeah. So this step is nothing but a justification of this, yeah. So maybe I should put it, yes, that's better. Now from here, so because this shows that A inverse HA Zn is basically H Zn, thus A inverse HA is contained inside H because Zn is contained inside H. So this is what we have, and this is for any H. So therefore we must have A inverse HA, a subset of H, proving H must be contained in H, A inverse. So this holds for any A lying inside here. Now observe that if A lies here, then A inverse also lies here, because A inverse will lie here, but if A inverse lies in H, then since H is subgroup, A has to lie in H. So therefore this conclusion also holds when we replace A by A inverse. Also similarly, one has H compose A inverse H A, which shows A inverse is a sub H. Now this together with this implies A inverse is H. That means A lies in the normalizer of H, but A does not lie in H. So therefore we obtain a point which is in the normalizer but not in H. Hence the normalizer of H is properly contains H. Yeah. Let me repeat the proof. So, for any A lying here and for any H, we see this is what we must have, because this side is nothing but this and this side is that, and that group is abelian, okay, and that group is abelian. Therefore, this is what we must have, and from that this follows, and that is how it goes. Okay. So, basically from 1 to 2, it is 1 to 2 is done. Now, from 2 to 3, so P with the, we have to show that each Sylow P subgroup is normal. Okay. That is again an application of what we have just proved, that is, so we will be now proving 2 to 3. If Pi is not normal, so the argument goes as follows: if Pi is whole G, then there is nothing to prove. Okay. If Pi is a proper subgroup of G, then we look for its normalizer, right? We look for its normalizer, and we have just obtained that in that case Pi will be proper subgroup of its normalizer. Okay. Now, so it will be now proper subgroup of its normalizer. Then we would like to prove that this is equals to G, then I will be done. If not, so let me repeat, so if Pi is proper, Pi is a proper subgroup of its normalizer, we would like to show this is whole of G. If not, then then again by the second condition, this is a proper subgroup, therefore it must be a proper subgroup of its normalizer. Okay. But let me tell you that this is not fine because of the following. So, small observation. So, just an observation which holds for any group. Let G be any finite group, P, and let us say P a prime divides G, and N is a, P is a P Sylow subgroup. Then normalizer of P, again the normalizer of that is nothing but this is itself, which I would like to leave as an exercise, but let me also tell you that the main observation behind this, that is that P is a normal subgroup of its normalizer, right? That is what follows from the definition, and therefore, and since P is normal in G, normal in this normalizer, so that means P is this is the unique Sylow P subgroup, Sylow P subgroup of the normalizer. Try to understand. So, because any other Sylow P subgroup of the normalizer will be a conjugate of P, but P is normal here. So, the unique Sylow P subgroup of the normalizer. Okay. And from that this is an immediate consequence. I leave the rest to you as an exercise. So, now let us come back here. If Pi is a proper subgroup of G, then we have this. So, then we must have this, but in general we should have equality here. So, that is a contradiction. Hence, we are done with the proof of 2 goes to 2 implies 3. Okay. Let me again just quickly recall. So, this is just if a Sylow subgroup, if Pi is G, then we are done. If it is proper, then we look, it should be a proper subgroup is normalizer. We aim to show that this is G. If this is not G, then this will be further then it will be further normal subgroup is normalizer, but for any p Sylow subgroup of any general group G, we see that if once we take the normalizer again, so that it does not change at all. Alright, so now we are supposed to prove 3 implies 4. So how to show 3 implies 4? So to see 3 implies 4, we have to do the following, the most obvious choice, that in one hand we have this direct product from here to G. We would like to consider the following natural map: x1 up to xk goes to the product x1 up to xk. Okay. Now we aim to show that this map is an isomorphism. So for that, what do we have to show? First we will show the following, that it's easy to see that for any I not equal to j, pi intersection pj is trivial, because this is order. So the orders of these two groups are co-prime. Okay. In not only that, something even more, that also along the same line it follows that yes, so what, okay. So from here it follows easily that if it follows that if x lies in pi and y lies in pj, then x inverse y inverse, look at this quantity. So by 3 pj is normal, so this quantity lies in pj, this is also lies in pj, so therefore this entire quantity will be inside pj. Looking at it from the other, on the other perspective, this lies in p1 because this lies in pi, because pi is normal, this is in pi, so therefore this is also in pi. So thus this lies in both pi intersection pj, which is trivial. This forces xy equal to yx. So what it shows is, if we take two elements from two different Sylow subgroups, they will always commute, and in view of this, it is clear that this is an homomorphism. So if you take another tuple y1 up to yk, then x1 up to xk times y1 up to yk, you can since elements coming from different Sylow subgroups commute, you can immediately bring y1 with x1, y2 with x2, and that's how we prove this is homomorphism. This is homomorphism. Now next we want to show that this is 1 1. So showing, in order to show this isomorphism, it's enough to show now it is 1 1, because here this side has, so both the sides have order same. So we now just show that this map is 1 1. How to see this map is 1 1? So again that's a routine exercise. So I will just give you the sketch. So suppose x1, x2, xn, xk is 1. You fix any I do not care. So since they commute this, so therefore you can write like x1 up to xi minus 1, xi plus 1, xk is xi inverse, okay, that you can write. Now observe that x1 is in p1. So therefore if we raise it to the power, some power, raise it to the power pi to the power alpha I, then this one, this quantity, this is going to be identity. So raising the left hand side to this power, let me put some j not equal to I. If we raise the left hand side by the, to this power, then the left hand side will be identity, right, because each xj will be 1 once it is raised to the power this. Okay, so this is basically an immediate corollary of Lagrange's theorem. So therefore xi inverse, the order of xi inverse must divide this, okay, but there is a problem, because order of xi inverse, or which is same as order of xi, that's a divisor of pi, that's a power of pi unless it is identity. So let me repeat, so the order of xi must divide this quantity, and therefore order of xi has to be 1, that implies xi has to be 1. Okay. So thus this shows that this map is a homomorphism, hence we prove from 3 to 4 and 4 to 1 has already done. Thus we have finished the entire, we have finished the proof of the entire theorem. So this is just an irregular argument considering the orders of the both sides. Okay. Once we have finished the proof, let me deduce an interesting corollary from this. So earlier what we have seen is like all finite abelian groups are nilpotent, in fact all abelian groups are nilpotent. Let's stick to let's focus our attention on the finite groups. So then we can have p groups which are not necessarily, we will see that p groups they may not be abelian. So thus like beyond abelian groups we do have nilpotent groups, and then we do have this classification. So in view of this theorem, it may seem it is quite tempting to say that we can thus determine all, we can thus classify all nilpotent groups because they are just the products of p groups, but unfortunately that is not the case, because classifying p groups is even classifying p groups is a quite hard job. But yeah, so but however when the groups have order smaller, then we can do something, in fact we will do. Now let us deduce a corollary from this. So let's take a divisor of order of g. A divisor of order of g will look it will look like this, right, where each beta I is less or equal to alpha I. Now corresponding to the order p to the power beta I, there exists a normal subgroup of pi. There is a normal subgroup of pi which is having this order, right, which is exactly having this order. Okay. Now therefore once if we take this normal subgroup, so this has order exactly same as this divisor, and of course since each pi is normal in each ni is normal in pi, so this has to be normal in g. So thus we see that some stronger version of the converse of Lagrange's theorem is Lagrange's theorem holds here, that is it says that which shows that every divisor of order of g, we do have a subgroup, in fact a normal subgroup having that order. Okay. So thus we see that for nilpotent groups we have the converse of Lagrange's theorems. Okay, so let me put it in this way, the converse of Lagrange's theorem holds. In fact a stronger version we proved, we do have normal subgroups of that order for nilpotent groups. For nilpotent groups, of course finite groups, converse of Lagrange's theorem holds. So therefore it's quite natural to ask whether this, so earlier we have seen that it's not true that for all groups the converse of Lagrange's theorem holds, namely A4 was such a group for which the converse of Lagrange's theorem does not hold. But here we see for nilpotent groups we do have this converse of Lagrange's theorem. So it is quite natural to ask that, and of course we know that A4 is a solvable group, right. So like it's a very natural question that whether we can like, okay, sorry, let me put it in this way, that of course from the example it is clear that this result cannot be extended to arbitrary solvable groups, because A4 is a solvable group where the converse of Lagrange's theorem does not hold. So it's natural to ask that up to which stage one can extend, up to what stage, how far this can be extended to any finite solvable group. This is what is the content of the following theorem, which we will not prove because it is beyond the scope of this course. So this is known as theorem by Philip Hall. Theorem due to P. Hall. You can see that this is in fact an extension of first and third theorems of Sylow. So here we have suppose G is a group having order Mn and M and N are coprime, GCD is 1, and of course G is solvable. So then the following things hold. So what are the things that one can have here? The first thing is there exists a subgroup of G such that order of their subgroup is n. Next, if H and K are two subgroups of G such that order of H and order of K are both M, then they are conjugate. Okay. So these are the you can see these are the extensions of first and third theorems of Sylow for solvable groups. The third condition says that if K divides N, of course K positive, and K is a subgroup of G with order of capital K is small k, then K is contained in a subgroup of order n. Okay. So for Sylow's theorem we have proved that every pi subgroup of G is contained in some Sylow pi subgroup. So this is the extension of that observation, the generalization of that observation for solvable groups. So thus we can see that the converse of Lagrange's theorem, which we have seen holds for any finite nilpotent groups, that does not of course hold for solvable groups because A4 is a counter example, but for solvable groups one can go up to that far, one can go up to this stage. Okay. Okay, so enough nilpotent and solvable groups we have done. Yeah. So we won't prove this because this is beyond the scope of this course. Now let's come to what we are talking about a few minutes back. That is, I just said that such a nice classification, that is every finite nilpotent group has to be product of P groups, that does not help us much to classify all finite nilpotent groups, because classifying P groups is a quite difficult task. So yeah, so when the order is large, it's very difficult to classify all groups with that order. However, when the order is small, we can classify them. So let me show you the classifications for groups of order p square and p cube. Well, when the order is p, then there is nothing to prove, this is cyclic. For p square we can do without much difficulty. Order p square, where p is a prime. So then we can also classify all groups of order p cube, but for that we need some more work. So there we will postpone that for later. So we will postpone that for later. Before that we just we will see some applications of Sylow's theorem. So after that we will come back to the classifications of groups of order p cube. Now let me classify all groups of order p square. So let G be a group of order p square, group of order p square. So if this is not cyclic, then every non-identity element must have order. So every non-identity element must have order p. Okay. So let pick any non-identity element x. So x must have order p, and this cannot be whole G. So therefore we can pick a y from outside the cyclic subgroup generated by x. So this y will also have order p. Okay. Now we will see that the following gives an isomorphism. So a typical element here looks like x to the power a for some a running from 0 to p minus 1, but that is not so important. In fact, for any integer a and b, y to the power b. So for any two integers, we can talk about this map. We will now prove that this map is a isomorphism. So both the sides have order p square, so it's enough to show its homomorphism and 1 1. So in order to show the homomorphism, we will proceed as we have done earlier. That is, we will first show that first let us observe that inside G this is trivial. This is because either it is going to be trivial because both have order p, there is going to be trivial, or the intersection, or so what can be the order of this intersection, either p or 1. So therefore thus it follows either trivial or both are same, but that cannot happen because y has been chosen from the outside. Therefore this is trivial. And one more thing, both the subgroups have index, the smallest prime, here the only prime dividing order of G. So therefore both of them are normal in G. So given this is the situation, now it is easy to see that for any a and b in Z, x to the power a, y to the power b, x to the power minus a, y to the power minus b. So since y this is normal, so this lies in this part lies in this cyclic subgroup generated by y, this is also in that subgroup. So this entire thing lies in the cyclic subgroup generated by y. Similarly, if we group the terms like this, we see this the same thing lies in the cyclic subgroup generated by x. So therefore this product lies in their intersection, hence it has to be trivial. Thus this shows that so thus this shows that okay, I think maybe I can yes, so x to the power ab is so any power of x commutes with any power of y. That's the main thing we have proved, that's the thing which we have proved now. So once we can prove this any power of x commutes with any power of y, from that it follows that this map is a homomorphism. Okay, this map is a homomorphism. Next we have to prove that this is 1 1. We just have to show this as the kernel is trivial. So what about the kernel? Kernel means x to the power a, y to the power b equal to 1. Bringing y on the other side, we see that both x to the power a and y to the power b both lies in the intersection which is trivial. Therefore therefore it shows x to the power a has to be trivial, y to the b has to be trivial, hence this map is 1 1. So it's easy to see, so let me again write it for you. So x to the power B. So both lies in the, because left hand side lies here, right hand side lies here. So this is trivial. That force says that both x to the power a equal to y to the power b equal to trivial equal to identity. Hence this is phi is 1 1, and then we are done. Thus we are done. And as an immediate corollary to this, we can talk about the nilpotence class of any nilpotent p group, of any p group. So recall that any p group is nilpotent. So how do we prove that? So this is what we are having. Okay, so that's well, yeah, so I should consistently maintain one notation. Yeah, so z to z, so z to z, then z3z, that's how it goes. So once at some point of time it has to stabilize. So you see that at every step the order might increase by a factor p, at least it increases by a factor p. So that shows that this can go, the strict containment can go up to nth stage, okay, up to nth stage, but then, so the maximum stage can appear when at each step the order is being increased by the factor p. So then there will be some, then we might have this situation where z to the zn minus 2g will have p to the power n minus 2, because p square, if that's how it goes, this has to be this. Now but then you see this is having order p square, so this is abelian, hence its center. So p, we have in fact proved that any g, if g is having order p square, then either g is isomorphic, is cyclic, that is isomorphic to z modulo p square z, or it is of this form, that is isomorphic to z modulo pz, z modulo pz. So every group of order p square must be this or this. So in particular they are abelian. So since this is abelian, so its center is going to be the whole group, therefore once you take it back, then you will get the entire group G. So then this implies Z n minus 1 G is whole of G. So that means that then at the in the n minus 1th stage it will achieve G. So thus it is clear that the G is of nilpotence class. At most n minus 1. Let me again slightly repeat that what might have, so in this upper central series, if the order at every stage the order has to increase by at least the factor p, if it increases further, so if suppose from some step to another step, if the order increases by p square or something, or some higher power of p, then certainly we will achieve G before n minus 1, I mean certainly we will achieve G before this step, okay. But if it only increases by the factor p at every stage, then we must have this, and then the immediate next step has to be the G. So therefore there is no way where we can have the strict containment beyond these many terms, okay, which follows from a corollary of this, okay. So thus we have classified all groups of, as I said that when for p groups when the order is smaller, then we can do some classification. In this lecture we will classify groups of order p square and p cube. This is the complete classification of groups of order p square. For p cube we need to do some work, we need some further for p cube we need to do some more work. So Therefore, let us postpone that for a while, and now let us move on to applications of Sylow's theorems. So, once these applications will be over, then I can simply come back to groups of order p cube. All right. So first let me remind you the Sylow's theorems. What are Sylow's theorems? If, I mean, in the usual notation, if is a finite group where these are distinct primes, then for every prime pi, for every I in 1 up to k, there exists a subgroup. For every I, there exists a subgroup having exactly that order. So, such a subgroup will be called Sylow pi subgroup. Remember that its order is the highest power of pi dividing order of G. Then the second one says that any two Sylow p subgroups are conjugate. So, for any prime, for any p equal to p1 up to pk, okay. And the third theorem says that, so let NP denotes the number of Sylow p subgroups for a p dividing order of G, then NP is congruent to 1 modulo p, okay. And of course, another one is also quite clear that NP divides order of G, because G acts on the set of all Sylow p subgroups for any given p. And second theorem assures that this is transitive. So, therefore, now this is the single orbit. So, the order of the orbit will be a subgroup of will be a divisor of order of G. So, these are the Sylow's theorems. Now, we are going to see a few applications of Sylow's theorems. So, the first application we are going to see is for groups of order of order 6. Okay. So, if G is a group of order 6, then what can we say that? So, by Sylow's theorem, it has a subgroup of order 2 and 3, right? It has a subgroup of order 2 and 3. So, let X be such that this has order 3 and these are cyclic groups. So, let X and Y be such that this has order 3 and this has order 2. Now, certainly this is going to be normal in G. So, what is there? This group has elements 1 X, X inverse. Next, now we can simply consider Yx, Y inverse. So, since this is normal, Yx, Y inverse will be here. It cannot be identity, either it will be X or minus X, X or X inverse. Okay. And now study them case by case. So, in this case is easier to see because we have an element of order 3, another element is of order 2, and Yx, Y inverse is X inverse. So, in this case, in the later case, G has to be D6, right? G has to be D6 because we have an order element. This follows from the classification of general dihedral groups. So, now let us come talk to the former one. So, this means X and Y commute. So, in the former X and Y commute, x and y commute, and in this case it is easy to see that this map is going to be an isomorphism. So, x to the power a comma y to the power b goes to x to the power a y to the power b. So, this we can prove this can prove following the strategies that we have adopted earlier. I mean, their intersection has to be trivial, x and y are commuting, so any power of x will commute with any power of y. So, this usual one. So, therefore, in this case this factor is isomorphic to z mod 3z, this is isomorphic to z mod 2z. So, thus we get in this case G must be isomorphic to z mod 3z, z mod 2z, which is further nothing but z mod 6z. Okay. So, hence we have classified all groups of order 6, either it will be the cyclic group or it will be D6, which is again D6 is nothing but S3. Okay. So, as an immediate application of Sylow's theorem, we prove that for groups of order 6 up to isomorphism there are only two choices, one is the cyclic, another one is non-abelian, that is S3. Of course, this classification you can do with bare hands, that is without getting into Sylow's, but using Sylow's we can do it in a much easier way, that is what we have done. Now, let us move to other groups. And of course, one more thing that here the situation you have a normal subgroup, another subgroup, and intersection is trivial. So, I mean, if you wish you can also do this by using recognition theorem for semi-direct products, but yeah, I mean without getting into that we can also do like as we have done there. Okay. So, next we will talk about the classification of groups of order p cube, p q, where p and q are distinct primes, with p less than q. So, let G be order group of order p cube, not p cube, p times q. By Sylow's theorem we do have subgroups of order p and q. Okay. And what are the divisors here? 1 p q, p q. Okay. Now, you can see that NQ, that is the number of Sylow subgroups of Q, it has to be 1, right, because P is the prime P is less than Q. So, NQ is 1. What does this mean? There is exactly one Sylow Q subgroup. Since all other Sylow subgroups are, since any two Sylow Q subgroups are conjugate to each other, then this forces that, so for any other, so there is a general observation that if NP is 1, then then H is normal in G, where H is the Sylow P subgroup of H is the Sylow P subgroup of G. This is because all other Sylow P subgroups are conjugates of H. Now, NP is 1 forces that all conjugates have to be equal to H itself. This exactly means that H is normal. So, this holds for a general observation that a Sylow P subgroup is normal if and only if it is unique. So, NQ is 1, that means K is normal in G. So, K is normal in G, H is there. Now, by recognition theorem it is immediate that for some phi this is what we are going to have, because K is normal, H is there, and order of Hk we can calculate this nothing but order of H times order of K by their intersection. Intersection has to be trivial because orders are coprime. So, all the required conditions are there, hence it has to be this. Okay. Now let us see what are the possibilities. So one thing is clear by this analysis, that every group of order p cube must be isomorphic to some semi-direct product of cyclic some semi-direct product of let us say this is isomorphic to z, this is isomorphic to z mod qz, and this is isomorphic to z mod pz. Okay. So one thing is clear, that any group of order p cube will appear as some semi-direct product of these two groups. What we have just, that is what we have proved, that if we are given any group of order p cube, then it has to be some semi-direct product of a Sylow q subgroup with Sylow p subgroup. So thus by classifying all possible semi-direct products, we can classify all groups of order p q for given primes p and q. Now let us see the following, that if assume p divides q minus 1, then what happens? Then once p divides q minus 1, then p does not divide q minus 1, then we see that np is also 1. This implies H is also normal. Okay. Now you see that in this semi-direct product, so what is phi here? So given a group G, phi is nothing but the phi of k is conjugation by k, right? So the copy of H and k inside this semi-direct product under this isomorphism, that goes to the copy of, that goes to H and k inside G. That is clear by means of the isomorphism. So if H is normal here, that means the copy of H here is also normal. Now in this semi-direct product, k is already normal. Now H is also normal. That means phi has to be trivial. It's trivial. Once phi is trivial, then this is in fact kh, so which is isomorphic to z modulo pqz. That is, in this case, if p does not divide q minus 1, then there is after isomorphism there is a unique group of order p cube, namely the cyclic one. Let me just repeat this argument, that so under this isomorphism, so this semi-direct product has a copy of H and has a copy of K. Under this isomorphism, they correspond to the subgroups, given subgroups H and K respectively. That is quite easy from the recognition theorem, which you have already observed. So therefore H is now normal in G, means in this, so H is normal here, that means its image, which is nothing but the copy of H, that is also normal. That forces phi has to be trivial, hence we have the cyclic structure. Okay, it is quite natural to ask what happens when p divides q minus 1, for which we have to, of course, we have to do some more work. Maybe we can, so I will quickly say that, and then we will just tell you what to do, and then the rest we will do in the next lecture. Case 2, namely p divides q minus 1. So in that case, ought k is like k, since k is isomorphic to z modulo kz, z modulo pz, ought k is isomorphic to ought z qz, ought z modulo qz, and there is second isomorphic, that, and this has order q minus 1, which is divisible by p. Therefore there is an automorphism let us say there exists an automorphism, there exists alpha in naught k of order p, right. So, yeah. So, either you can deduce that from the Cauchy's theorem or maybe a special case of Sylow's theorem and then passing it, and then what we have done for p groups, that if a prime divides the order of some group, then there has to be an element of that order. That, as I said, either you can deduce that using Sylow's theorem and what we have done for p groups, or you can do it directly by Cauchy's theorem, which I have put in one of the assignments. So, whichever you like, you have an isomorphism of order p, and then the rest is a quite routine thing. So, then H is there, right. So, if denote, let X be a generator of X. Now, sending X to this alpha, we can talk about we obtain a non-trivial homomorphism from H to ot k, right, H to ot k. So, therefore, which results in a non-abelian group. So, then since it is non-isomorphic, this has to be non-abelian. Okay. So, when p divides q minus 1, we can indeed have a non-abelian group of order p cube. Okay. And how is that done? By picking a element of order p from this odd group. Now, you see that the way we have done that depends upon the choice of alpha. Now, of course, the choice of alpha cannot be unique. So, the natural question is, if we choose different alphas, whether the subgroups that we are going to obtain in this manner will be isomorphically different. So, for that we have to prove a theorem on the isomorphism of semi-direct products, which we will be doing in the next lecture. So, the next lecture I will continue with the isomorphism theorem that will ensure that whichever alpha we choose, isomorphically we will get the same thing. Okay. So, this lecture is now over.